Welcome to The Explainer. Today we're digging into a fascinating new idea in cosmology. And it all starts with a really simple but kind of profound question.
What if the very fabric of space-time remembers? Not like, remembering what it had for breakfast, but what if it remembers the absolute chaos of its first moments? Imagine a kind of physical imprint, a geometric fossil left over from the dawn of time itself.
Look, our standard model of the universe, it's amazing. It works incredibly well. But there are a few really stubborn puzzles that just won't go away. So today, we're going to explore a new hypothesis that takes a totally fresh look at these problems. It's not about rewriting the laws of physics, but about wondering if we've missed a clue from the universe's very first moments.
Okay, so before we get to the new idea, we need to set the scene. We've got to look at the cosmic cold cases, right? These are the big, nagging mysteries that tell cosmologists, hey, we don't have the full picture just yet.
All right, first up, it's a classic. When we look out at galaxies, the stars way out on the edges are spinning ridiculously fast. So fast, in fact, that based on all the stuff we can see, all the stars and gas, they should just be flung out into the darkness of space. This is actually the main reason we think dark matter exists, some invisible halo of stuff providing the extra gravity to hold it all together.
Then there's this new puzzle, thanks to the amazing James Webb Space Telescope. It's finding these huge, fully formed, mature-looking galaxies way back in the early universe. We're talking less than 1 billion years after the Big Bang. Our models just don't predict that. It's kind of like planting an acorn and coming back a week later to find a giant oak tree. Something's not quite right.
And here's the really big one, the Hubble tension. It's a cosmic mystery that's driving scientists crazy. When we measure how fast the universe is expanding, using light from right after the Big Bang, we get one number. But when we use stars in the universe closer to us, today, we get a different, faster number. And the thing is, both measurements are super precise. They're both right, but they don't agree.
So our best explanation for everything is something called the ΛCDM model. You can think of it as our recipe for the cosmos. And it works great, except the two biggest ingredients, dark matter and dark energy, make up something like 95% of the entire universe. And we've never actually seen them. Ever. We only know they're there because we see their effects. It's a bit weird, right?
So, what if there's another piece to this puzzle? Something we've just overlooked. Not a replacement for dark matter, but maybe a little something extra. An extra layer of detail. And that brings us to the core idea we're talking about today. This is the big idea. It's called the Imprinted Curvature Hypothesis, or ICH for short. And the thinking goes like this. Maybe spacetime isn't a perfectly smooth blank canvas. What if it still carries faint geometric scars from the day it was born?
Okay, space-time memory, geometric scars? That sounds cool, but what does it actually mean? Well, let's try a simple analogy to make sense of it. I want you to picture the universe as a giant bedsheet. Right after the Big Bang, it was a crumpled, messy ball. Then, this thing called cosmic inflation happened, which was like grabbing the corners and stretching that sheet out at an unbelievable speed, making it almost perfectly smooth and flat. But, and here's the key idea, what if some of those original, really deep wrinkles didn't get totally smoothed out? What if they got, ironed into the fabric of space-time? Faint, permanent creases that are still there today, subtly influencing how gravity works? Now, where would these creases even come from? Well, this isn't just a random guess. The hypothesis points to real physical processes that were happening in those first chaotic moments. Things like tiny quantum jitters in space-time itself, or massive, messy bursts of energy after inflation ended. Any of these could have created the initial wrinkles that then got frozen into place.
All right, so let's say the universe has these faint, leftover geometric creases. How in the world does that help us solve those big cosmic mysteries we were talking about just a minute ago?
Well, the key here is that these imprints might offer a geometric assist in explaining these puzzles. So for those super fast spinning galaxies, maybe a subtle background curvature adds just a tiny bit of extra gravitational grip, helping dark matter do its job. For those big early galaxies, maybe some of those creases acted like cosmic potholes or seeds, giving matter a head start to clump together. And for the Hubble tension, well, what if large-scale wrinkles in spacetime are subtly warping our view, like looking through old glass, making the expansion rate just look different depending on where we measure? Okay, I have to be absolutely crystal clear on this next point. It's really important to understand what this hypothesis is not.
This isn't some wild idea meant to throw out everything we know about physics. In fact, it's actually a very conservative idea. It's not trying to get rid of dark matter or dark energy. It's not changing Einstein's theory of general relativity at all. All it's saying is, hey, maybe we should think a little more about the universe's starting conditions. Maybe the fabric of space-time wasn't perfectly smooth from the get-go.
And you can really see that here. When you put IACH side by side with other ideas like modified gravity, you see the difference. Modified gravity theories want to change the fundamental rules of the game. ISCH works completely within the existing rules. It's not about new physics. It's about a more complex cosmic history, a history written right into the geometry of space.
So, is this all just a cool story, a neat thought experiment? Or can we actually go out and, test for it?
And that's the best part. This is real science because it's testable. You can prove it wrong. The hypothesis predicts that these ancient creases should leave a very specific, faint pattern on the light from distant galaxies as it travels towards us, something we can look for with gravitational lensing. Our next generation of telescopes will be powerful enough to either see these subtle geometric patterns or show us they're not there at all.
And that really brings us to the final, fascinating thought here. What if the answers to cosmology's biggest questions aren't hiding in some exotic new particle we haven't found yet? What if the secrets have been there all along, etched into the very fabric of the universe, an ancient memory from the Big Bang, just waiting for us to finally learn how to read it?